Hello everyone, this is Joe here with Joe Talks, and today we are going to talk about EV charging stations. And I want to go over the EV charging station that I purchased and that I use every day. And this is going to be for the level 2 hardwired charging station. So not a 110 plug-in, not a plug-in to your dryer outlet. This is a hardwired into your breaker box of your home. And I'm going to talk a little bit about the charger I picked, why I picked it, and then I'm going to go over the installation of that charger. Now, before we get started, just like all of these videos that we do with electrical and that are revolve around electricity, if you are not comfortable doing electricity, don't do this project. So if any of this sounds unfamiliar with you or to you, or you're not 100% confident that you can do electricity safely, go hire a professional. Don't try to do any of this stuff on your own. But you should still watch the video because at least this will give you some knowledge and allow you to talk kind of intelligently with your contractor that's going to do the install for you. Okay, with that said, the EV charger that I chose was the Wallbox unit. And so I purchased this off of Amazon. And this unit comes in two different options. It comes in a 40 amp option and a 48 amp option. Now, I drive a Chevy Bolt and it only charges at 32 amps. So the unit I chose was the 48 amp option. But it's more than what I needed for the Bolt. But the reason I went ahead and went with that higher amperage is because I wanted something that was capable of charging a Tesla. So Teslas charge at 48 amps, I think. And so this is more than enough to get to charge a Tesla. So I was kind of future planning for any EV upgrades I might make in the future. So this is going to be an install for that 48 amp unit. Now, the reason I picked this unit, I kind of shopped around quite a bit. The one thing that really sold me on this unit was the fact that they advertised what they kind of call share charging, I think is what they call it. But basically it's where you can daisy chain multiple units together. And so what I thought was cool about that is I won't have, if I wanted to add another unit, like say for example we bought a second EV for my wife to use, I wouldn't have to run a new power circuit from my relay box over to the charger. I can just daisy chain a second unit off of the first one, and then that same unit will share that power supply. And what I thought was kind of unique and interesting is that they've got logic built in that will split that power evenly. So like say for example you've got two cars charging, it will split the power to both of the cars even though it's lower than what the car's max charge rate will be. And then when one car is done, it will re-divert that power back to the remaining car at a full power capacity. So I thought that was really nice. And so again, kind of gives me the ability to upgrade later on down the line. So with that said, let's get into the actual install and talk about all the things that we would need to do to get this wired into our control panel, or keep saying control panel, into our breaker box, and run wire and get it all landed. But more specifically, making sure we get the right size breaker and the right size wire, and running it properly from the box to the unit. Okay. One of the first things we need to look at when we're laying out our electrical circuit to put this EV charger on is to consider what kind of load this circuit is going to see. So when you talk about NEC codes and you dive into that whole process, it is really kind of a spaghetti string mess. I mean, the NEC code can sometimes be really complicated and hard to follow, but there's a few basic concepts that we can try to understand and stick with as we move along. So one of those first things is we need to consider if this is a continuous load on this circuit or if it's kind of an intermittent load. And so if we think about what an EV charger does, technically an EV charger isn't completely continuous. It kind of ramps up and down, but for what we're doing, we're going to kind of consider when we say it's a 48 amp draw, we're going to consider that a continuous draw throughout the charging cycle, even though technically it's not. So if we look at the rest of this circuit, I'm making this a dedicated circuit. So there's no other outlets on this circuit. So the only device on this circuit from the breaker box to the charger is the charger. So it is kind of a single device type circuit, dedicated circuit, if you will. And so if you think about the charger, when we plug that into the car, it's going to run, and it's going to run for some time until obviously the car's charged up. So when you read the NEC code, when they talk about low voltage stuff or low amperage stuff, which is what we're dealing with, they consider a continuous load is any load that runs longer than 3 hours. And so when you think about the EV charger, that charge can take longer than 3 hours. If you have a completely depleted battery, that could be putting a continuous load on that circuit. Not knowing how the software works in the charger, I can't assume that there's any breaks, even though there probably is. We're going to consider that to be a continuous load. And so when I talk about these NEC codes, please don't rely on my knowledge. Want to disclose, I'm not a professional electrician, so do your own research. Make sure you validate and double check all the things I'm telling you, because things may have changed from the time that I made this video. But anyway, with our circuit, we're talking about a continuous charge. So the first thing we have to do when we design our circuit is we have to consider what size of a circuit breaker we're going to use. And so there's a couple ways we can do this. We can manually calculate it, which is what we're going to do, or the instructions do have a lookup table, and so we'll look at that as well, just as kind of a secondary source. But we want to kind of understand how we get to that number. So there's something in the NEC code, and I believe it is in section 310, but don't quote me on that. Anyway, it's kind of roughly considered the 80% rule. And so what that means is when we select a circuit breaker, where we have to size that circuit breaker so that the circuit, or the amperage in the circuit, is 80% of the capacity of the circuit breaker. So let me just read the verbiage from the NEC code as at the time of this video making here. So it says and this is for overcurrent protection of conductors. And so this is for your fuses for circuit breakers. It says, the general rule to protect conductors against overcurrent is by using fuses or circuit breakers rated no higher than the conductor's ampacity. The overcurrent protection device guards the conductor's insulation against the damage that excessive currents and overloads and short circuits can cause. And so basically, just in a nutshell, your circuit breaker is meant to protect the conductor, or in other words, protect the wire. So if you're not familiar with electricity, the concept is to keep the amperage in the wire less than what the capacity of the wire can carry, is what we're trying to get at here. So NEC section 210.20 establishes the rating or setting of the overcurrent protective devices to protect the branch circuit, conductors, and equipment. Okay, it says similarly to section 210.19.A1, which is, I think, the section that governs the actual sizing of wire and stuff. It says for conductors' ampacity, section 210 states that where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the rating of the overcurrent device shall not be less than the non-continuous load plus 125% of the continuous load. So, what does that mean? Well, kind of what we just talked about. We are assuming a 48 amp continuous load because we're potentially running for more than 3 hours, and so we have to have a circuit breaker that is 125% of 48 amps. So Let me pull up a calculator and we'll see what that is. So 48 amps times 1.25 is a 60 amp breaker. So that means that we need to use a breaker size of 60 amps to adequately protect the circuit that runs continuously at 48 amps. So that's kind of the first step of our process, is to select the breaker. And so we will install that breaker at 60 amps. And if we look at the actual installation instructions, it says that this is going to be a 240 volt supply. So we're going to have a 2-pole 60 amp breaker. And so that's what I've got installed, is I think it's an Eaton breaker, 60 amps. And then if we look at the wiring diagram in the installation guide, you'll see that there is a red wire, a white wire, so those are your 2 power supplies, and then the green wire for the ground. And then the ground acts as the neutral. In this case, they're both kind of one and the same with this design, even though technically that's not what we normally have in housing residential wiring, but that's the way that this charger is specified to be wired. So we have 3 wires that are going to run to the charger, the 2 power, and the ground. And so we know now that we need to have a 60 amp breaker. So the next step is to determine what size wire we need to run between the breaker and the EV charger. So what we're going to do is we're going to pull up a ampacity chart. Now you can find these ampacity charts online just about anywhere. Just do a simple Google search for wire ampacity and you will see a chart that looks something like this. And so if you'll notice on this chart, there are some different options down the left side, and that is your gauge of wire, obviously wire gauge size. And then we have some numbers across the top that correspond to temperature. And so a lot of times these temperatures can kind of trick people up a little bit about what these temperatures mean, what they represent. And so the first thing you need to understand is that these temperatures, the 60 degrees, 75 degrees, and 90 degrees Celsius, that is not ambient temperature. That is not surrounding temperature. What those numbers are telling us are that at the amperages specified in this table, this is the amount of heat that will get generated in the wire. So these temperature specifications are really kind of describing what kind of insulation is on the wire. So you'll notice up here you've got in the first column for 60 degrees C wire, NMB, UH or UF and B rated wire. And then in the 75C, you've got some different classifications, THW, THWN. And then in the 90 degree, you'll see some different designations, THHN, THWN-2, so on and so forth. And so those are really classifications of what kind of insulation is on the wire, which will result in what the temperature rating is at the given amperage for the given gauge. So, and that's important because we have to take into consideration heat generation when we size our wires. And so if we go back to our calculation on our circuit breaker, we determined that we need at least a 60 amp circuit breaker. So we have to make sure that we have wire that is capable of carrying current that is larger than the circuit breaker, because you want the circuit breaker to break before you exceed the ampacity of the wire, technically. And so what we can do is we can look at this table, we can come down through here, and we say, okay, we know we needed 60 gauge or 60 amp wire. Now, if we look in the NEC code under temperatures, there is a section in the NEC code that talks about terminations, and it talks about looking at the heat generation. So let me just read that to you real quick. So says for equipment rated for 100 amps or less, which is us because we're at that 60 amp level, or less, marked for 14 gauge or 1 gauge conductors, which is we're in that range. It says, unless listed and identified for use with higher temperature rated conductors, the conductor ampacity is based on a 60 degree C rating, even though the conductor rating allows for higher temperatures such as 75 or 90 C. And then it goes on to talk about equipment rated over 100 amps. It doesn't apply to us, but basically what that means is when you're talking about wire, in a nutshell, it says assume 60 degree, right? So that is going to be the gauge that will yield the lowest heat rating, right? So, and that's important because what will happen is if you put a higher temperature rated wire on a conductor that's not rated for the same temperature, if you pump that much, the max current for that insulation, you could overheat the connection point between the two elements. So like a wire going into a circuit breaker is what for our application, that's what we're specifically looking at. And so if we go back to our table and we look at 60 degrees C, we can see that we ideally would need a 4 gauge wire, right? So 4 gauge at 60 degrees C is capable of carrying 70 amps, right? So we know that if we had a 4 gauge wire that was at least an MM-B, that breaker would trip before we ever overheated the wire. So ideally in this application we would want 4 gauge copper wire, at least in the 60 degree category. However, we have a problem with this installation. So one of the things that I did like about this install is that it does come with a very good installation manual. And there is a section in that installation manual where it talks about electrical wiring. So there is a whole page where it walks you through how to hardwire the system in. Now there is a section over here where it talks about the circuit breaker selection. So just to confirm our calculation, it says here for a 48 amp system, you need a 60 amp breaker, right? And so that's exactly what we calculated using the 80% rule with 60 amps. And now we just determined that to pick the proper wire, we need 4 gauge wire. But let me show you what the problem is. In their instruction manual, when they talk about electrical wiring, if we look down here in step 3, it says use copper conductors only within the wire size range of 10 to 6 AWG. Well, how can that be? According to our calculations, we need 4 gauge wire. Well, they've designed this thing that the terminals won't accept 4 gauge wire. It says 6 gauge is the highest or the largest wire that it will accept. So now we're in a pickle because we can't use 4 gauge wire. So what are we going to do? Well, let's go back and look at our wire right now. So the other mistake that you might make if you were going to wire this thing, you may come back and say, okay, well, let me just pick the 6 gauge wire, right? It says 6 gauge. We should just be able to go get 6 gauge wire, right? So if you go to Lowe's and you go to look up some 6 gauge wire, probably one of the first things you're going to see is a wire selection that pops up. And so this is what I've actually seen on Lowe's website, is you get a 633 Romex wire. And you think, okay, well, that's 633. It's got my white, my red, and my ground. That's exactly what I would need, right? Well, look, this is NM-B. So this is NM-B rated number 6 wire. Well, if we go look at the ampacity chart, you see that 6 gauge NM-B is only rated for 55 amps. So that means we can't use that with our 60 amp breaker because the wire will get too hot. Right? So what are we going to do? Well, what's the next size up wire? Well, if we look at What if we got something in the 75 or the 90 degree range, right? So you can always kind of upsize your wire. You just can't downsize it. So you can always downgrade a higher temperature rating as long as you don't exceed the temperature rating of the circuit breaker. So, so if we look at some other options, what do we have when we go to Lowe's and we look up 6-gauge wire? Well, you're probably going to find the next option, right, if you're just going to Lowe's to get wire, is you will see something that looks more like this, right? So this is a 6AWG single-stranded copper wire, but it's THHN wire, right? So this is still 6-gauge wire, but it's got a different kind of insulation on it. So let's go back and look at our ampacity chart. So what do we have with THHN? It's rated for 75 amps at 90 degrees. Okay, well, now we have to start thinking about, okay, what is our circuit breaker rated at? So if you go look at a circuit breaker, so if you look at a 60 amp 2-pole Eaton circuit breaker, you'll see on the side, you'll see a designation that looks something like 60 degrees Celsius / 75 degrees Celsius. So what that means is that is a dual rated temperature rating for that circuit breaker, which means you can use 60 or 75 temperature rated wire. So so if we look at this, we can look at 6-gauge wire and we can downgrade that to, we can go in the down direction, so we can downgrade that to a 75C rating, and we see that as long as we keep the amps at 65 amps or less, the temperature will not exceed that 75 degree C rating. So what that means is we can still use this THHN wire in our circuit, and as long as the amperage stays at least 65 amps or less, it won't get too hot. So that means that the wire's sized right, adequately. It means that the insulation is adequate, that it won't generate too much heat in that wire. In other words, the insulation won't hold too much heat in the wire. It'll still dissipate heat and not overheat the connection between the wire and the breaker. And so, because our breaker is a 60 / 75 degree C rating, we can use a 75 rating in the table. 6-gauge 75 rated wire is 65 amps, so that's greater than our breaker capacity, which means the wire is going to be protected. So now that is an option. So what we can do is we can use this single-stranded 6-gauge wire, and so we would have to run 3 wires of single-stranded 6-gauge between our breaker and our charger. So that would be the better solution for something you're going to find at Lowe's to use in this application. So at this point now we've got a 60 amp breaker, we've got 3 strings of single-stranded 6-gauge wire. You can probably get by with a lower amperage for the ground maybe, but I'd just stay with 6-gauge for everything, just the way I did it. Now there's one other thing though, because now we're not using Romex, we're using single-stranded wire, so there's also an NEC code that says you can't, in a residential environment, run single-stranded wire in open air. So now we have to be in a conduit, right? So that's the third factor we have to figure out, is what size conduit. So we know the breaker size, we know the wire size, now we just got to figure out what size conduit. And so the conduit I'm using is just a Schedule 80 PVC pipe. And so you can go online and you can find a table for wire conduit size for THHN wire for Schedule 80 pipe. And so we have 3 wires, so we need to find a wire or a diameter pipe that will work. So if we come over here to 6-gauge wire, we come down, we find 3. So our conduit size for our run needs to be at least 3/4 inch or higher or larger pipe. So I'm not running any other wires, any other circuits through this conduit, so I can just use 3/4 inch Schedule 80 pipe. So now at this point we know breaker size to be 60 amps, double pole. We know the wire size to be 6 gauge THHN single stranded wire, and get the proper color code right, so red, white, and green. And then we have our conduit size, so we have to run those 3 wires in conduit, and we know the size of that conduit has to be at least 3/4 of an inch. So with all those elements, we can pull our wire, run our conduit, and then land the wires. And now, as far as the connection inside of the EV controller, we're not given a whole lot of information about that connection, anything to do with its heat ratings or anything. We are given that it's a NEMA 50-2, I think, which is just an environmental rating saying that it's watertight and dust type. So at this point, I'm kind of making an assumption that that connection inside that breaker box is going to be okay as far as the temperature rating goes. But in reality, we're really only hitting 48 amps. We're keeping our wire and our conduit and everything all protected size-wise. So that's kind of really the unknown, is that connection inside of that EV connector or EV charger. So kind of making some assumptions there. I hate to do that, but kind of have to. Don't have any other options. So that is how I've wired this circuit in, and that's how I've sized the breaker, sized the wire, sized the conduit, and made the run. And the other thing is, my run is less than 100 feet. I think when you start doing things over 100 feet, you have to start taking voltage drops into account, so keep that in mind. I'm not that long. I think my run's only 25 feet, so I'm okay. But anyway, that is it. And so here is a picture of my installation. One thing you'll notice at the box, I've got the 3 wires exposed, and that's just because when I did this install, it was on a holiday weekend and Lowe's was closed, and I needed to get some 90-degree fittings, and I didn't have access to them. So that became one of those things I was going to do later that got put on the back burner. And as you see, I still got my 3 live wires, right? That's how most projects tend to go. Seems like you get them 90% done, and there's always that last 10% that hardly ever gets done. But keep in mind, I do have to go back and get those wires enclosed in conduit. But at least in this photo, you can see the wires that got ran, see the conduit. So anyway, that is it. And I hope this helped. And again, if you're not comfortable doing any of this stuff, do not try to do it on your own. Hire a professional, but at least use this video to kind of be knowledgeable about the topic, so you can talk intelligently with your contractor. So anyway, if this helps, please help me out. Again, this is Joe Talks. Like, subscribe, it's free. Please help me out. Anyway, that's it. And until the next one, all right, thank you.